Okay, we'll be talking about work today, chapter 8a. And so in physics, we're going to define work as being the force times the distance. And after this, you should know that work is a scalar product of force and displacement, and solve problems involving the concept of work. Distinguish between the resultant work and the work of a single force, and define the spring constant and calculate the work done by a varying spring force. Three things are necessary for the performance of work. There must be an applied force, there must be a displacement x, the force must have a component along the displacement. So if force does not affect displacement, it does no work. So as we can see here, you have a force going sideways, and the Earth does force of gravity going downwards, but there is no work even though there is displacement. So if the displacement is to the side, the applied force is upwards, weight is going down, and because it's in a different direction, they're perpendicular to each other, then there is no work. So work is a scalar quantity, means that it doesn't have a direction, and it's a product of the displacement x and the component of force f of x in the direction of the displacement. So f of x times x is equal to work. To do positive work, the force and the displacement must be in the same direction. For example, if the force is 40 newtons and the displacement is 4 meters, then simply by multiplying we get 160 newtons times meters. So one of the units of work is newtons times meters. And the other unit would be a joule. So 1 newton meter equals 1 joule. So the work here would be 160 joules. What about negative work? Well, notice that the displacement here is to the right, but the force of friction is to the left. Then the friction force F opposes the displacement, and so the force of friction would be negative 10 newtons, and the displacement x is 4 meters. So if we multiply them together, we get negative 40 joules. So the net work is the sum of the individual work. So we have a positive force in the positive direction with the 160 joules. We had the force of friction at negative 40 joules. So when we add them together, we take the difference because we're adding the negative, and we get 120 joules. Resultant work is also equal to the work of the resultant force. So if we find the net force is just the force applied minus the force of friction, so that's 40 minus 10, which is 30 newtons times the 4 meters, that gives us 120 joules, which is exactly what we got before. So what we can do is we can find the work due to the force applied, subtract the work done by friction, and that gives us our net work. Or we can find the net force first, such as in this screen, and then multiply it by the displacement. So what about at an angle? Well, at an angle, we just need the component of force that's along the x direction. In this case, theta is 60 degrees and the force applied is 70 newtons. So in order to get the work, we take the 70 newtons of the force applied times the cosine of the angle times the displacement to get 420 joules. Only the x component of the force does the work. So only the component of the force that's along the displacement does the work. So procedure for calculating work: draw and sketch, establish what is given and what is to be found, draw a free body diagram choosing positive axis along the displacement. Here's an example. And then find the work of a single force from the formula. The resultant work is a work of the resultant force. How about this one? We have a lawnmower and it's being pushed a horizontal distance of 20 meters by a force of 200 newtons, directed at an angle of 30 degrees with the ground. What is the work of this force? So we only want the component of the force that's acting along the x direction. So we're going to take the cosine of that. So here we have work is f cosine theta x. Plug in our numbers and we get the work. Note work is positive since f of x and x are in the same direction. Contrast this to the force of friction in which they were opposite directions, so it was negative. 40 Newton force pulls a 4 kilogram block a horizontal distance of 8 meters. The rope makes an angle of 35 degrees with the floor and a coefficient of friction of 0.2. What is the work done by each acting on the block? Each work done by each force acting on the block. So here we sketch it out, and we know that it's pulling, here P stands for pulling, 40 newtons, displacement of 8 meters. Here's the force of kinetic friction, here's the angle of the force, and then the mass that we're moving. So now we draw a free body diagram. So we have the normal force, as always, going up, pulling force at 35 degrees, the force of friction opposing that motion, and then weight going down. And so the work is just F cosine theta times x. So we could find the work done by each force. First, we can find the work done by the pulling force, which is P cosine theta times x. And so it's 40 newtons times the cosine of 35 times 8 meters, which gives us 262 joules. Next, we find the normal force N and the weight W. So each makes a 90-degree angle with x, so the works are 0. So the normal force and weight don't do any work. Lastly, we find the work done by friction, and that's force of friction is the coefficient of kinetic friction times the normal force. So now we know that n plus p cosine of theta minus mg is equal to 0. So we can find the normal force here, and this right here should be sine. So let's go back and see if we can correct this, because this is wrong. So what this is supposed to show us is that the normal force plus the sine of this angle minus the weight is equal to 0. So that the normal force is the weight minus the sine. This should be the sine. And here, magically, it's corrected. So the normal force is the weight minus the y component of the pulling force. So the weight minus the y component of the pulling force. So it would correspond to this part of the pulling force. And that would give me the normal force, which I can multiply by mu to find the force of kinetic friction. So again, these down here should be sine. And those are the summation of the forces in the y direction right here. So now I can find the work done by friction. So it's 3.25 newtons times 8 meters, which is negative 26 joules. Notice it's negative because friction is opposing the motion. The motion is to the right, friction is to the left. To find the net work, and notice here it is cosine. Cosine of 180 is -1, and that's how we get that negative sign. So the resultant work is the sum of all the works. And so the first one we have is the work of the pulling force, normal, and the weight, and then lastly that done by friction. And so the net work would be 236 joules. How about our famous block on an incline? What is the resultant work on a 4 kilogram block sliding from top to bottom of the 30-degree inclined plane? So here they give us h is 20 meters and mu sub k is 0.2. So we can find the net work and find the work of the three forces. And work is F cosine theta times x. So we can find out what x is by using trigonometry. So in this case, x is the hypotenuse, h is the side opposite the angle, so we can use sine. So sine of 30 is equal to h over x. And that means that x is equal to, x is equal to h over the sine of 30, which is 40 meters. So the distance that it's going to go down here is going to be 40 meters. So we want to find the work of weight, and remember it's the mg sine theta from our previous problems. In this case, they use the complementary angle, which is 60. So mg cosine of 60 is the same as mg sine of 30. So we can find the work done by the weight mg, and that's equal to 784 joules. And that's positive work because it's along the displacement. So gravity's pulling it down, and x is going down in that same direction. So next we find the work of friction force F. So we need to find N first. So there's our free body diagram. And we know that N is equal to mg cosine of theta, which is 30 degrees. And that's what N is, 33.9 newtons. If the force of friction is mu times N, we just multiply that across and it's 6.79 newtons. So now to find the net work, we take the force of friction, multiply it by 20, because that's the distance that it's going down, by the cosine of 180, because it's in the opposite direction of r. So notice the F is 180 from r, which is the displacement. And that's going to give us our negative sign. We have the work done by friction, which is negative. And what is the work done by the normal force? Well, the normal force doesn't do any work because it doesn't go anywhere. And so all we have to do now is add up the sums of the works. So we have weight is positive 784, friction is negative 272. The force done by the work done by the normal force, is 0 joules. So we just take the 784, subtract the 272, and we get 512 joules. So note the resultant work could have been found by multiplying the resultant force by the net displacement down the plane. So we could have found the net force by taking the force of the weight in the direction of motion minus the force of friction, and then multiplying that by the displacement. So what about the graph of force versus displacement? So let's assume that we have a constant force F, and it acts through a parallel displacement delta x. The area under the curve is going to be equal to the work done. So work is equal to F times delta x. So what is the work done by a constant force of 400 newtons moving a block from x equals 1 to x equals 4? Well, it's just going to be F delta x, which is 40 times 3, and that's going to give us 120 joules. So the area of a force versus displacement graph gives us the work. So the area of a force versus displacement graph gives us the work. What about work of a varying force? So our definition of work applies only for a constant force or an average force. What if the force varies with displacement as with stretching a spring or a rubber band? So in this case, you can see that the force is going to change with the displacement. As you pull the spring further out, the force is going to be stronger and stronger. So recall Hooke's law. When a spring is stretched, there is a restoring force that is proportional to the displacement. F equals negative kx. The spring constant k is a property of the spring given by that. And remember that the units are going to be newtons per meter. So work done in stretching a spring. Work done on the spring is positive. Work done by the spring is negative. From Hooke's law, we have F equals kx. And so the work is going to give us the area of the triangle. And the area of the triangle is 1/2 base times height. In this case, it's 1/2 times x times the average force. So we can use the idea of the average force because the force varies linearly with x. So if we wanted to find the work, we find the area of a triangle. So the work done on a spring is 1/2 kx squared. Compressing or stretching a spring initially at rest. Two forces are always present, the outside force F out on a spring and the reaction force F sub s by the spring. Compression, force out does positive work and the force of the spring does negative work. So if you compress the spring, you're doing positive work on it and the spring is doing negative work. When you're stretching it, you're also doing positive work and the spring is doing negative work. A 4 kilogram mass suspended from a spring produces a displacement of 20 centimeters. What is the spring constant? Well, stretching the force is the weight, so it's going to be that 4 kilogram mass times gravity, which gives us 39.2, so that's our force. And we have our displacement, which we have to convert from 20 centimeters to 0.2 meters. And now we have our spring constant, which is 196 newtons per meter. So read another way, to stretch the spring 1 meter, it would take 196 newtons. What work is required to stretch the spring with K equals 196 newtons per meter from x equals 0 to x equals 30 centimeters? So remember, work is 1/2 kx squared, and we have K as 196, and then x is 30 centimeters, but there's 100 centimeters in a meter, so it's 0.30 meters. Calculating out, it gives us 8.82 joules. So that's how much work would be required to stretch that spring. And in stretching it or compressing it, it would be the same amount. The work to stretch an additional 30 centimeters is greater due to a greater average force. So if I wanted to stretch it a little bit more, it's already stretched some, but the force is going to increase because of the greater displacement. So it would take more work than the first 30 centimeters. If the initial displacement is not 0, the work is given by 1/2 kx sub 2 squared minus 1/2 kx1 squared. So in general, it would be the area under that part right there. So it's just the change, as we'll learn later, in the potential energy. So here's a summary. Remember that the work is a scalar quantity, and the component of force has to be in the same direction as the displacement, and that's where we get the cosine. And always draw what we're doing. Do a free body diagram and find the work of a single force from the formula, and the resultant work is the work of resultant force. So always draw a free body diagram, and work is negative if a component of the force is opposite the displacement direction, such as the frictional force. Work done by any force that is at right angles with displacement will be 0. So if the angle is 90, then the work done by that force is 0. For resultant work, you can add the works of each force or multiply the resultant force times the net displacement. So for springs, remember Hooke's law, F equals kx, and k is equal to F over x. Remember that the negative just tells us that the force is in the opposite direction of the displacement x. The spring constant is the force exerted by the spring per unit change in its displacement. The spring force always opposes displacement. This explains the negative sign in Hooke's law. And then work to stretch a spring. So if the initial position is 0, we can just use 1/2 kx squared. If it's not, we just take the difference of those two, which we see here. So remember that two forces are always present, the outside force on a spring and the reaction force by the spring. Compression, if you compress it, you're doing positive work and the spring is doing negative work. If you're stretching it, you're also doing positive work and the spring is doing negative work. However, once it's compressed and you let it go, the spring begins to do positive work.